Good to see you. Thanks for having me. I'm especially happy to go up after Patrick, who already did all the stuff explaining why freedom of speech is important. He mentioned Article 19 of the Declaration of Human Rights. There's also an Article 12 that says that you have the right to actually be private when you do these things, like express yourself. So we don't have to spend so much time on discussing whether anonymity is valuable or not, because it's a fundamental part of freedom of expression, which in part is important for democracy. So with that out of the way, here's my full disclosure slide. I work for SUNET. Here's my boss. It's great. I've been there for many years and working for SUNET and NORDUnet. Been able to work a lot on Tor as still being employed by NORDUnet and SUNET. So what I'm saying today is also colored by my affiliation with the other two organizations down there, like Tor Project, which is producing the software and the network that I'm going to talk about today, and DFRI, a Swedish digital rights organization that is running some capacity for the Tor network. I'm on the board of directors of both those two other things, so when I say positive things about Tor, remember, it's from a person who really, really likes this. So think a bit about what I'm saying and try to be a bit skeptical if you are that kind of person. So, before today, how many of you had heard about a thing called Tor? I see many, many hands. Okay, so if you ever use Tor, keep your hands up. And so I see at least half of the audience have been using Tor. How many of you have ever run a relay in the Tor network? So I see 1, 2, 3, 4, 5. I see at least 12. How many of you are still running a relay in the network? Wow, that's great. I see at least 3, 4 hands. That's a nice audience. So what is Tor? For those of you who didn't hear about it, it's an anonymity network. It's an overlay network on top of the internet, where volunteers run relays, as we call them. There are ordinary computers on ordinary internet connections, and they relay traffic in a 3-hop circuit setup that I'm going to explain a bit later. When you say Tor, some people mean the organization. There is actually a non-profit US-based organization, 501(c) something, tax deductible. You can donate your money there if you're a US person, and you get your tax back or something. We are employing about 20 people today. We have about 10 contractors right now, and we have another 30 people working as volunteers with core things. So you could say that we are a 60-person organization by now, paying half of them and having the rest for free. We get our money mostly from various research funds, like NSF was mentioned earlier today, National Science Foundation in the US. They pay some of our salaries. We have other programs. CEDA is one of the former donors to Tor, and we also receive other things from, like Google, send us some of code people that they pay for making Tor better. So we have a large set of funders, but lots of the funders is actually positioned in the US today, and that is something that we would like to change. And not only because being dependent on one source is bad, but also because diversity in funding is as important as diversity in relay operators or diversity in users for an anonymity network, and for the trust in the network. Sometimes when you say Tor, you might mean the community. We have a large set of researchers. Most of them are based in the US or Germany. They do lots of research on how can you actually do this thing on top of TCP on the internet, which is kind of a crazy thing, which also is the reason for the title of this speech, which was an imperfect solution to a serious problem, which is running things on top of TCP is not always perfect from many point of views, as you might know. These are helping us with trying to fix this, but mostly they are trying to break Tor. We have lots of good researchers trying to figure out how to de-anonymize Tor users. And we have a deployed large network with about 2 million daily users. It's hard to count. It's an anonymity network, so we cannot really count them, but we have ways of doing estimates of how many users we have daily. We think we have about 2 million. But the nature of the software and the network and the openness makes it actually really useful for doing real research on. So researchers kind of love this, and that is why we can also be good at protecting our users because we have a good relationship with researchers to do the hard work for us. Then we take their things and we put them in the hands of our developers. Most of the people that we pay are developers. Most of the people that we try to recruit are software developers in one way or the other. And they will have to produce the software, mainly one program that does many things. It's a local proxy on your machine, and it's also a relaying network, like a VPN, but you make several hops. We have the relay operators, about 7,000 relays in the network today, which means thousands of people volunteering to run this software on their machines, spending time on keeping it updated and stuff like that. We have a support function, or we have many support functions, not only for users who need to figure out how to use this, but also for all the people who are trying to do this. Relay operators don't get so much support, but software developers, of course, do. I mean, they get paid. They need some infrastructure to run their stuff on and all that kind of things. So Tor can mean community, lots of things. Tor can also mean the protocols that we are using for connecting all these relays and to connect your client with the relay and to get out on the internet to reach internet in an anonymous way. There is a repository with all of our specifications and our proposals in an RFC-like style. We have like you propose something, it goes through a queue with where you get it from idea to proposal to implemented to closed and stuff like that. The source code is, of course, open. Everything is open and free. We are publishing all the source code under a BSD license, and have been doing so since the very beginning. I think Tor, the little T-Tor program, counts some 200K lines of C code by now, which is a kind of scary thing. So we're also starting to move into a memory-safe language. We have picked Rust just recently for a number of reasons, partly because it's easy to actually replace subsets of a large program in Rust and see if it still works. So the final thing, when you say Tor, you might also mean the network. This is a picture of about half of the 7,000 relays that we have in the network today. They are grouped on AS number because I think this crowd would actually find that interesting, that we have, I don't know how many, but like a large portion of our relays are in 3 AS numbers, in 3 ASs. You can make this graph go in many different ways. You can sort it on network blocks or something else. And metrics.torproject.org is the source for statistics or information about the relays or users in the network, which is very useful for us to measure how the network is running, but also to be able to see if we make changes, what happens to the network, what happens to performance and stuff through the network. So, what kind of problem are we trying to solve? Back in the 90s, when we used to have crypto wars and stuff, we finally came through and was able to encrypt the contents of the stuff that we sent. And nowadays, actually, we do. Lots of the traffic on the internet is actually encrypted, much thanks to TLS, much thanks to easier way to get certificates today for HTTPS connections, but also because of lots of messenger applications are doing end-to-end encryption today. So we are in pretty good shape when it comes to protect the contents of your communications. But we are not so good at protecting the metadata. So the metadata is the information about who talks to whom and when and how much. And that is not, someone used to say, there was a former president of the US who said, it's only metadata, when the first Snowden revelation came that they were collecting lots of phone calls, phone lists of who is calling who. And he said, it's only metadata. We are not looking into your phone calls. We are not listening. Well, metadata is problematic in itself. If you got enough information about who is talking to who and when, you can pretty much identify a person. And that is what former NSA chief said on a panel in Stanford 2014. And one of the best examples I think I saw was, how do you know when there's a war coming on? you look at the number of pizza delivery going in and out of Pentagon. That is traffic analysis. You see, if they're eating lots of pizza right now, there's probably something going on. Okay, so Tor provides 3 functions, and the first one is probably the most known one. You fire up something called Tor browser, which is a fork of Firefox, and then you start typing in a URL, and then you visit your favorite site, dn.se or svd.se or whatever you are looking for, and you come there not with your own source IP address, but you use someone else's IP address. That is probably the most known part of Tor. The second part is that it happens to be that, and it wasn't actually designed from the beginning, but it happens to be good for breaking censorship in parts of the world where you block lots of resources. You might not be able to block the whole Tor network, and therefore, if someone can reach the Tor network, they can use that to reach the rest of the network. And I think people here would call that connectivity, so that you can actually use internet. The third is something called onion services. It used to be called hidden services, where you can publish stuff anonymously. So you can publish a website, or you can publish any service, basically. And one interesting thing that has come up the last couple of years is that it has some properties, onion services, that makes it interesting for things like Internet of Things and other things like that, because they are self-authenticating addresses. So the address actually is a subset of a hash of the public key that only the server holds. So there's no need for a CA system or anything broken like that. You can actually, when you type in this, okay, very horrible name, but it is a name that actually ties into the secret key at the other end. But it also is the great net puncher. You can actually put your service behind any number of any types of net, and you will still be able to be reachable from another place on the internet. So these are the 3 things that we provide. One hop is what we used to call a VPN, or what is called a VPN. This is basically, Alice wants to go to Bob, she connects to a VPN service, and then that service will go to Bob, and Bob will not see Alice's source IP address. And none of the people on the right side of the relay in the middle will know that Alice is talking to Bob. They will only see that someone is talking to Bob. And if you are on the left side, if you are Alice's ISP, you will only see that she's going to a VPN provider. I would argue that this is not enough, because if anyone could actually surveil the middle box here, the VPN, they could correlate in and output traffic relatively easy. And if your adversary is looking into, or is the ISP of that VPN provider, or is putting some pressure on that VPN provider, or maybe your adversary is running the VPN, as is the case in some places in the world where VPNs are actually forbidden, but nevertheless they actually exist, and you can wonder what is the price for running a VPN in a country where VPNs are forbidden. So the solution is to have 3 hops rather than 1. And imagine that R1 to R5 stops at R7300 instead, or even higher. It should be hard to be able to correlate input traffic and output traffic, because it should be hard for you to be able to watch both R1 and R3. This is basically a source-routed network. So Alice, and this is important, Alice has to be the one who chooses the path to the network, because if the adversary can make her choose relays that the adversary has control over somehow, either by running them themselves or by being able to look at input and output traffic there, they can correlate input and output just as they can with a simpler VPN solution. This is something that this problem is intrinsic to all low latency anonymity networks. Other kinds of networks where you have a high latency, where you can buffer things, like, for example, a mixnet, where you can send email by sending email to one place and it stays there for some time and then it sends a chunk away. It's a high latency network. They don't have the problem with time correlation of input and output traffic. Now, if we didn't have any encryption here, it might not be so valuable, because then R1 could you see that traffic is going towards Bob, or R3. The key here is that R2 is isolating R1 from R3. So R1 can see that Alice is trying to talk to someone, and R3 can see that someone is talking to Bob, but cannot see whom. The trick here, and this is the reason it's called onion routing, is that what Alice does when she signals a path through the network, she negotiates keys with these 3 hops. And then before sending her packet over that is going to Bob, she wraps it in 3 layers of encryption. So first wrapping it in the key that she has with R3, and then the one with R2, and finally the key that she has shared with R1. When the packet reaches R1 has the key to the outmost layer and can peel that off, like the skin of an onion. That is basically why it's called onion routing. So when the packet then leaves R1, it comes to R2, and R2 is the only one who can decrypt the outmost layer here. It goes to R3, who can decrypt the final layer, sends it to Bob. Bob sends the request back. Let's say it's an HTTP request. The response comes back to R3. R3 encrypts again in the blue key, and it goes back all the way. And Alice has to wrap up 3 layers before serving the resulting page from Bob to the browser. So that is the basic of this, and it seems to work pretty well. So I mentioned statistics and metrics. We do collect lots of metrics because we need to be able to figure out how we're doing. And we need to be able to see what's happening when things go wrong. We have a couple of weird things happening here. For example, spring 2014. Anyone remember something happening spring 2014? We lost lots of relays, or we kicked out lots of relays from the network. Heartbleed. Heartbleed was a bug in OpenSSL that left the possibility for someone to grab the key material from your SSL, basically. And so we gave people some time to actually upgrade their stuff, and if they didn't, then we kicked them out. And therefore, we had a drop. But then we have great relay operators who said, hey, why is my relay not in the network anymore? And we told them why, again, and then they just upgraded and came back. So we were back again in, I don't know, 3 months or so. Another weird thing, I'm talking about the relays up here, the red thing. There's also the blue line, which is something called bridges. They are like relays, but they're not public. They're only semi-public, and the idea is that you can use a bridge instead of the ordinary relays in the network if you're in a blocked place, or if you're if you are in a place on the internet where someone is blocking you from connecting to the public relays in the network. Then there are something called bridges. They are semi-public, and it's supposedly hard to get all of them, all 2,500, or how many are there? Yeah, 3,000. But it's easy to get 3, or something like that. This is a tough game. China is really good at enumerating our bridges, so bridges doesn't really work in China anymore, but it works in many other places. Maybe at your workplace, maybe not this crowd, but some other crowds work at places where they do these things, blocking TLS, because it's kind of dangerous for the employer to have you talk privately to the internet. In those places, you could use bridges for connecting. We had a large drop in bridges late last summer because we switched the bridge DB, which is the place where we keep the bridges, and we couldn't make all the bridges connect to the new bridge immediately. If you're interested, there are lots of things that you can read out of all the graphs at metrics.torberg.org if you're interested in how the network works and what it does. Here is the capacity of the network. We are announcing some 225 gigabit per second. It's not a large network. I mean, it's not a lot of capacity. We're using about 100 gig. We're using about 100 gigabit per second. Utilizing 100 out of 225 is pretty good. The gap here is, of course, important because we are trying to not overbook the network. The clients would like to choose the fastest path through the network, so the client would like to choose only the fastest relays. We are measuring the relays continuously and reporting that in a way that clients can look at that and pick based on speed. But not only speed, because you don't want to just pick the 3 most speedy relays in the network, because then that's kind of non-anonymous. You would like to have some spread. And the more fast relays we have, the more fast relays a client can pick from. So I'm pretty happy with the gap between utilized and advertised bandwidth today. We also measure end-user performance. This is, as was it Daniel who said, horrible, 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 900 milliseconds to get a page in the 95th percentile. We are here downloading 50 kilobytes per second. It takes over 1 second. That is the downside of using this network. It's not very impressive to be able to give 50K in over a second. And if you go to 5 meg, I think you will have to wait for 10 seconds. Now, this is one of the price you pay for being anonymous. We like to put this down, of course, but there are some physical limitations. You have to hop to three places. All these 3 places have they have an upper limit on how much they can push, of course, not only because of their connection, but also because of the lot of crypto that is going on in each and every of the relays. Not to mention that we are running everything over TLS. So the link-to-link protocol between the relays is TLS over TCP, obviously. And then we try to run things over TCP. And we have the same thing as Daniel told us earlier, that head-of-line blocking, if we have 1 drop, we are multiplexing lots and lots of things on single TLS connections between relays. So if we have 1 drop here, everybody has to wait. There has been some discussions, or there have been some experiments actually, using other transport protocols, like one experiment using libUTP in userland, and another one is to actually use QUIC. And the QUIC experiment seems interesting. I don't know where it is today, but it's an interesting future, I think. So that is the network part. Network part is one thing, but the application layer is the next big thing. I mean, your browsers are meant for tracking you. That's kind of what the business model is. And the browsers are not very good at protecting your privacy. So what Tor has done is to actually fork Firefox and patch up a lot of things and add a lot of features that makes it reasonably secure to actually use the web anonymously. It's not a nice job to have to. I mean, we are at least 4 people working full-time on just keeping up with the 6-week cycle, release cycle of Firefox. And since about half a year, there has been a tremendous effort from Mozilla to actually do what they call patch uplift. So they have actually included most of the patches by now that Tor project has made to Firefox in the last 5 years. So we think that in the next, or the release after that, we will actually not have to spend so much time when they release a new version of Firefox in order to give our users a version that is actually reasonably secure. So that is great. We're pretty happy about Mozilla at this moment. Unfortunately, none of the other browsers are nearly as interested in trying to protect their users against tracking. I guess Google has a specific problem with that because their whole business model is to track people. So I guess that's kind of easy to understand why they are not so good at that. So this is my final slide. You can help if you want to, but you first have to admit that we built the craziest tracking thing ever built in history of mankind. It's not really nice. I mean, in the beginning it was great. I mean, packets came and went, and they came back even if things broke because we had the source address in the packet. That's kind of brilliant, but we kind of had to bolt on security, and now try to bolt on some sort of privacy on top of that is actually not very easy. But the other thing, since some of you are operators and you know lots of things about networks, you might be interested in helping people run relays on the network, because without no relays, there's no network, and we can just pack up and go home and continue being tracked. Network operators are typically, some of the network operators are sympathetic to the idea and good at discussing these things, but as soon as they get abuse complaints, they kind of get, this is, if they have very low margin on the stuff that they're selling, they don't want to deal with abuse. It's actually eating up all their profit if they have to have people who respond to abuse things. Other ones are like, yeah, okay, here, we just forward the abuse to you and you can deal with it. And they will have to take the risk that they have their network block being dirty somehow because the kind of traffic going out there is not the kind of traffic that they used to have. Other operators are just not interested at all. But there are also things, you don't have to run an exit relay on your network. You can also run a middle relay. The 3 hops thing, you can configure your relay to be only the first 2 hops, and then you never expose your IP address for being the exit, and you never get any abuse complaints for that. If you are software developers, if you are into doing things in an open source project, you can, of course, just contribute by doing that, or run your own relay, of course. And finally, if you are researchers, and if you're interested in overlay networks, or if you're interested in privacy in particular, we have lots and lots of good research stuff that is actually going to see some use. That is, I think, one of our greatest selling points to researchers. It's actually pretty easy to get something that is being deployed in the real world. So with that, I think if there is anything, because I covered kind of lots of things in a very short time. I guess someone...
So we're running quite short of time. If there's one quick question, we have time for a quick one. Will you be at the social this evening?
I will be at the social. So if there's anything that you want to ask that you think is not, suitable for a large crowd, please find me.
Preserving anonymity.
Mm-hmm.
Very nice.
Of course.
Okay.
Great.
Quick question over here with the microphone, please.
Hi, I'm Lars from IDG. What is your view upon that the Tor networks has been used by shady people? What?
Yeah.
You know what I mean?
Yeah. So I should start asking, what is your view on the... I've heard that the internet is used for horrible things. No? Okay. That's a misunderstanding. So yeah, I think it is, of course, as is lots of other technology. And it's tempting to go say, well, we have to take the good with the bad. Like, there is also tools, and a knife can be used for cutting up bread or cutting up your wife or your husband or whatever. But there's actually one thing that is a bit different here. The bad guys are doing great without Tor. If you have the resources, if you can spend the money, or if you are willing to commit a crime, it's not so hard to be anonymous on the internet. You steal someone's identity, you manufacture identity if you're a nation state, you spend lots of money, you break into some computers, you just use them. There are botnets, you can buy them, they are cheap. So if we shut down Tor tomorrow, internet crime wouldn't go away. Far from it, so I think that's my answer.
Okay. Please join me in thanking Linus and approach him for more questions at the social this evening.
Please do.